All right, welcome. Today, we're going to take a little tour through the super fascinating world of machine learning. We're going to pull back the curtain and really demystify how machines actually learn by looking at their different learning styles. You can kind of think of it like meeting a bunch of different students, right? Each one has their own unique way of figuring things out. So, the big question is, how do we even get a machine to think? Well, it all kicks off with a simple question, just like this one. For decades, we had to tell computers exactly what to do, line by line. But how on earth do you write code that just says, this is a cat? The short answer is, you don't. Instead, you teach the computer to learn for itself. And that, right there, is the magic we're going to get into today. So, here's our game plan. We'll start with the biggest idea of all, learning from examples. Then we'll check out a few different flavors of learning, through probability, by looking at your neighbors, and even by asking a bunch of questions. We'll also get a quick peek at how machines can learn like a brain, before we wrap it all up by figuring out how you choose the right tool for the right problem.
Okay, so how do machines really learn? The whole foundation is built on this one core concept called inductive learning. This is the big idea, the one that powers pretty much everything we're going to talk about.
Inductive learning sounds fancy, but it's really just a formal way of saying learning from examples. It's exactly how we all learned as kids. You see a robin, then a sparrow, then a pigeon, and pretty soon you start building a general idea of what a bird is. Well, machines do the exact same thing, but instead of seeing birds, they see data.
The whole process basically breaks down into 3 simple steps. First, you just feed the machine a ton of labeled examples. That's what we call training data. So for a spam filter, that means thousands of emails that are already marked spam or not spam. Second, the algorithm just churns through all that data looking for patterns. It might notice, hey, emails with words like free or winner seem to show up in spam a lot. And finally, it takes that rule it just learned and uses it to make predictions on brand new emails it's never seen before.
Okay, and this is where it gets really interesting because it shows the difference between how machines learn, that's inductive, and how we often think in logic puzzles, that's deductive. So deductive reasoning, that's your classic Sherlock Holmes stuff, right? You start with a big rule, like all men are mortal. Then you apply it. Socrates is a man, therefore Socrates is mortal. It's all top down. But induction, that flips the script entirely. It's bottom up. It looks at tons and tons of specific examples to build the general rule. And honestly, that's the secret sauce. That's what makes machine learning so incredibly powerful. All right, let's meet our first learning style. Think of this one as the statistician of the group. It's an algorithm called naive Bayes, and it sees the entire world through the lens of probability and odds. So the naive Bayes classifier uses this famous statistical rule, Bayes' theorem, to figure out the probability of something happening. But it makes one huge simplifying assumption, and that's where the naive part comes in. It just assumes that all the features it's looking at are totally independent of each other. Now, in the real world, that's almost never true, but making that assumption is what makes this algorithm incredibly fast and efficient. So how does this actually work for filtering spam? It's a few steps. First, it looks at all your old emails to get a baseline. What percentage of your emails are usually spam? That's its starting point. Then it looks at the evidence. How often do words like free or winner pop up in spam compared to your normal emails? Finally, it combines that starting belief with the new evidence to make a final, updated prediction on any new email that hits your inbox.
So here's the bottom line, the big trade-off. Naive Bayes is lightning fast and it works shockingly well, especially for things like classifying text. But its core strength, that naive assumption, is also its biggest weakness. Because, let's be real, words like win and free are definitely more likely to appear together in a spammy email.
Okay, let's move on to our next learner. Meet the social networker of the machine learning world, K-nearest neighbors, or just KNN. This algorithm pretty much lives by the old saying, you are who your friends are.
Now, KNN is what's called a lazy learning algorithm. And it's lazy because it doesn't really build some complex model ahead of time. Nope, it just memorizes the entire data set. That's it. Then, when a new, unknown data point comes along, it just looks around at its closest neighbors to figure out what it is.
And that K, what does that stand for? It's just the number of neighbors you decide to ask. You could look at just the single closest neighbor, where K equals 1, or you could ask a group of the 5 closest neighbors, where K equals 5. Figuring out the right K is actually a huge part of making this whole thing work.
The process is really intuitive. A new point shows up, the algorithm then measures its distance to every single other point in the dataset. Then it finds the K closest ones. Those are its neighbors. And finally, it's just a vote. If most of its neighbors are Class A, well, it gets labeled Class A. Simple as that.
And this really shows you the trade-off with KNN perfectly. On one hand, it's super simple to understand. But on the other hand, because it's so lazy and has to calculate all those distances for every single new prediction, it can get really, really slow and computationally expensive, especially when your dataset gets huge. Our third learning style is the detective. A decision tree works a lot like a detective on a case, asking a series of simple questions to narrow down all the possibilities until it finally cracks the case. A decision tree is pretty much just a flowchart. You start at the very top, at the root. Each little box or node asks a question about one specific thing, like, is the income over $50,000? And each branch that comes off it is a possible answer. You just follow the branches down, answering questions until you hit a leaf at the bottom. And that's your final prediction. Let's just walk down a path to see how it works. Let's say we want to predict if someone's going to buy a car. The first question might be about income. If the answer is yes, we go down that branch. The next question might be about age. If the answer to that is no, we follow that path, and boom, we land on our prediction. This person is likely to buy a car. It's just a clear, logical path to an answer. Now, the biggest plus for decision trees is that they are so easy to understand. You can literally just look at it and see the decision-making process. But their big weakness is something called overfitting. They can create a flowchart that's so perfectly tailored to the training data that it completely fails to generalize to any new data. It's kind of like a detective who gets so obsessed with one tiny clue that they totally miss the bigger picture. Okay, our final learner takes a totally different path, one that's inspired by the most powerful learning machine out there, the human brain. We're talking about neural networks. These are the engines behind everything from self-driving cars to AI art, and they learn by creating these complex, interconnected webs of understanding all on their own. So without getting lost in the weeds, just imagine the network has layers of specialists. When you showed a photo of a cat, the first layer of specialists is just looking for simple things, like lines and edges. The next layer takes that info, and its specialists start looking for combinations, corners, curves, basic shapes. The layer after that starts spotting things like eyes and ears. And this keeps going until the final layer can say, with confidence, yep, by putting all these pieces together, I'm seeing a cat. This process of building complex understanding from simple parts is what lets neural networks solve problems that other algorithms just can't touch. So, we've met the statistician, the social networker, the detective, and this ultimate brain-like learner. So, which one's the best? Well, the real answer is, it depends. Each one is a tool, and each is designed for a very specific job. And this little table gives us a great summary. Naive Bayes, which is all about probability, is the absolute go-to for spam filtering. KNN, based on closeness or proximity, is awesome for things like recommendation systems, finding things that are near what you already like. And decision trees, with their super clear logic, are perfect for fields like medicine, where you absolutely need to understand why a decision was made. The key takeaway here is matching the algorithm's strength to the problem you're trying to crack. So we've just barely scratched the surface of how machines can learn from examples, from probabilities, from their neighbors, and from simple questions. And it's already completely changing our world. But it does leave us with one final, really powerful question to chew on. Now that we've unlocked this incredible ability to teach machines, what's the most important thing we should teach them?